Hello and welcome to Precalculus lesson number 25. In this lesson, we're going to learn about exponential functions. As it turns out, many natural and man-made quantities either increase or decrease at an extremely fast rate, and the polynomial expressions that we're familiar with, where the base is a variable and the exponent is a constant, even though they do increase at a significant rate, they don't increase or decrease fast enough to capture the fastest types of natural and man-made growth or decline. What we need to describe that kind of growth is a group of functions called exponential functions, and the difference with them is that the variable, instead of being in the base position like the polynomials we're familiar with, is actually in the exponent position. This minor switch from changing the place of the base and the exponent, like for example from x squared to 2 to the x, is going to create a really large difference in the way that the function grows, as we'll see on the next screen. Okay, so here we have two tables. In one, we're looking at the way the function x squared grows for non-negative values. It's significant, like for example, when x is 0, we have 0, 1, 1, and then it starts taking off pretty well. Like when x is 2, we get 4, 3, 9, 4, 16, 5, 25, etc. We can see that it's growing pretty fast, but now look to the right at what happens when we switch x squared to 2 to the x instead. Now when we look at this function, notice it takes off kind of in a similar manner to x squared does, right? Up to about this point. From here, this one really takes off. Notice like 2 to the 5 is 32, 2 to the 6 is 64, 128. By the time we get to 10, 2 to the x has really left x squared in its dust. So basically, if you think of this as a really good runner, this one is a major sprinter. I mean, there's a huge difference in the way that these two functions grow. So let's go ahead and formally introduce the exponential function. The function f of x equals b to the x for b greater than 0 and b not equal to 1 and all real numbers x is called the exponential function. The domain is going to be all real numbers and the range is all positive real numbers. We'll see why that is in a minute. A couple of points about the restrictions we're placing here. We need b to be positive because we want the exponential function to be well defined for all real values of x. So for example, if we were to allow b to be -4, for instance, notice that for x equals 1/2, we would get f of 1/2 equals -4 to the 1/2, which is square root of -4, and that is not a real number. So for this not to happen, we went ahead and put the restriction that b should be positive. And of course, the reason we need b not to be 1 is that otherwise we end up with a function like f of x equals 1 to the x, and we know that any power of 1 is just 1 itself. So this would collapse down just to a constant linear function. And we don't want that to happen if it's going to remain a viable exponential function. So that's the reason for those two restrictions. In order to graph exponential functions, we'll basically set up a table of values and plot like with any other function. This f of x equals 2 to the x is often referred to as the reference exponential growth function. Then the reason we emphasize growth is because sometimes exponential functions can describe decline as well. So in this case, we're looking at an exponential growth situation. And if we just pick a few values, like here are the x values, -3, -2, -1, all the way up to 3. we just plug in. So for example, 2 to the power of negative 3, as we know, is just going to be 1 over 2 cubed, which is 1/8 by the negative exponent law. For negative 2, we get 2 to the negative 2, which is 1 over 2 squared, which is 1/4. Negative 1 gives us a half, etc., all the way up to 8 for y values. So when we plot those points and graph it, we get this really continuous and smooth, extremely fast growing function. And this is with just the base being 2, of course. And now you can see that all x values are in play in giving us the graph of this function, even the ones that are extremely to the right of this point and very large values. Remember, this keeps going, so eventually any x value you pick will have a y value associated with it for this graph. So the domain is all real numbers. Now you can see the values of the outputs, as you can see from the table, even whether you're plugging in negative values for x or positive, they never become negative or even 0. So notice that this curve, even though it looks like it's touching, that's just a limitation of technology, but it actually never crosses the x-axis. So we call the x-axis a horizontal asymptote for this graph, which means this graph will come arbitrarily close to, which is another way of saying as close as you want to get it, basically, to the x-axis, but it will never actually touch or cross the x-axis. Another thing to pay attention to is this point 0,1, which is very interesting given that all these exponential functions, regardless of the value of b, once you raise them to the power of 0, are going to give us 1. So they're all going to go through that particular point. Now let's take a look at what happens if we increase the value of b. See, we're going from 2 to 4 to 10 to 100. Notice what happens basically is that the growth becomes faster and faster. And however, interestingly, notice the domains will all be the same, all set of the set of all real numbers. The ranges for these simple types will also be the same. We'll look at some transformations of these exponential, the basic exponential function later, where the range might change by lifting, etc. But for these, the domain and range all the same. It's helpful to take a look at all the functions we just saw on the previous screen, all put on the same Cartesian coordinate plane. And again, you can see here how they all go through 0, 1, and we can see how the x-axis is a horizontal asymptote for all of them. And what we want to look at now is what needs to happen to b so that this growth suddenly shifts and become a exponential decay, as it's called, situation. Okay, so as it turns out, when the base is like the previous example 2 or any number larger than 1, you end up with an exponential growth scenario. If the base is less than 1, but remember, we can't just leave it there because we want to make sure it remains positive. So we say if the base is between 0 and 1, so we don't want it to go, the base to be smaller than 0, because then it would become negative. And if you recall, we want the base to be positive. So we talk about base values being greater than 1 or between 0 and 1. And never 1, remember, because then it would collapse down to a constant function. So when the base is between 0 and 1, and of course 1/2 is a value between 0 and 1, if you notice, this is exactly what happens. So when you plug in -3, for example, you end up with 1/2 to the -3. And remember, we had a rule that if you have a fraction to a raised to a negative power, you can flip the fraction and change the exponent to a positive one. So we end up with 8. -2 would give us 4. -1 would give us 2. 0 would give us 1, etc. So you see, in this case, the values are decreasing very rapidly. And you can see that beautifully depicted here. Again, x equals the x-axis itself, whose equation is y equals 0, is a horizontal asymptote for this graph. And it behaves very similar to the other one, except in the fact that it is decaying very rapidly rather than growing. The domain and range are once again the same as the previous situations that we already saw. This time we can look at what happened if we decrease the size of the base, keep making it smaller and smaller. We know that 1/4 is smaller than a half, 1/10 is smaller than both, and 1/100th, of course, is smaller than all of them. And notice what happens is that the decay becomes faster and faster as you go from larger base to smaller base in the 0 to 1 category. The domain and ranges do not change because you still define for all real numbers, and you still only get outputs that are greater than 0 in this case. Again, if we take a look at all of those on the same graph, you can see they all still go through 0, 1, and you can see how as we go to smaller and smaller bases, the decline, we should say, becomes faster and faster. These fall faster and faster. Now, sometimes exponential functions are given to us with a negative exponent. So we need to remember these 3 negative exponent rules from our previous experience with exponents, and they're simple enough, but you just need to remember them. If you have x to the -n, that becomes 1 over x to the n. 1 over x to the -n in turn becomes x to the n. And if you have a fraction raised to a negative power, as we saw earlier, you can flip the fraction, reciprocate it, and then change the exponent to a positive value. The same, of course, the opposite of that value. Because of the way that we defined the original exponential function without having a negative exponent, before we can determine whether each of these is an exponential growth or decay function, we want to make sure that we've written the expression of the function using positive exponents. So we're just going from left to right with these 4 functions, and we're going to decide whether they represent exponential growth or decay without graphing, solely based on the values that we see. All right, for the function f1, we can see that clearly the base is 5, which is certainly greater than 1, and there's no negative exponent to deal with, so therefore this is definitely an exponential growth curve. For the second one, we can see that 4/5, which is the base, falls between 0 and 1. Therefore, this would be an example of an exponential decay. For the third function, f3 of x, we need to first write it using positive exponents. So we know that f3 of x equals 3 to the power of -x. And we know that we can write that as 1 over 3 to the x. And in turn, we can go ahead and write that as 1/3 to the x. So the reason this can happen, of course, is because, as you know, if you have x over y, to the n, that's equal to x to the n over y to the n. So of course we can write 1 as 1 to the x. So we're using this rule going from right to left when we go from this step to this step, and we've replaced 1 with 1 to the x. That's why that can happen. All right, so now that we've written it in a form that uses positive exponents, no negatives in the exponent, we can see that the actual base is 1/3. So we make the conclusion that since 1/3 is between 0 and 1, this is going to be an exponential decay curve. You see how important it is to do that, because otherwise you may look at 3 and erroneously assume that, oh, 3 is greater than 1, so this should be exponential growth, which is not the case. Once again, here we notice that we have a negative exponent on the fourth function, so we go ahead and write f4 of x using the rule we saw earlier, that if we have x over y to the negative n, that's the same as y over x to the n. So we notice that we can do that here and say this is equal to 2/3 to the power of x. So once again, we notice that once we do the proper conversion, the 2/3 falls between 0 and 1. Therefore, this is also representing an exponential decay function. All right, if you recalled when we graphed the parabola y equals x squared, which we call the reference parabola, we learned that we can move that graph by changing its equation. Basically, we applied certain changes at the input x level, and that caused certain changes. Then we applied some changes at the entire f of x or y level, and that had other effects. Now we can do exactly the same kind of transformations with y equals b to the x, and we'll take a look at that now on the next screen. These are exactly in line with the kind of transformations we saw in the case of parabolas. For example, if we change the equation of y equals e to the x to y equals 2 to the x minus 3, this is going to have the effect of taking the graph of y equals 2 to the x and moving it 3 units to the right. If you recall, when you change the x to x minus a number, then the shift is actually to the right. If we do the change from y equals 2 to the x to y equals 2 to the x plus 3, that's going to be a shift of 3 units to the left. These are called horizontal translations or shifts. Now, if we bring the change at the entire y or f of x level, meaning we take the entire function and add a number to it or take away from it, that's going to bring a change at the y level. So we're going to be moving it up or down. So for plus 3, of course, we're going to move it up 3 units. For minus 3, we're going to move the graph of y equals to the x down 3 units. When we multiply by a constant like 3 here, we're going to actually bring a change at the y value again. We're tripling the outputs. The output, instead of being 2 to the x, is being 3 to the times 2 to the x. So this is going to be having a vertical stretch effect, of course, by a factor of 3. But remember that when you vertically stretch a function, its graph actually becomes horizontally more compressed, as was the case with x squared that we saw previously. So when this value here is larger than 1, then it is going to have the effect of a vertical stretch, which is simultaneously equivalent to a horizontal compression. When the value here of the constant that you're multiplying by the original function is between 0 and 1, then it's going to have a compression effect vertically, which of course horizontally the graph will get more stretched out. Now, if we have that factor multiplied at the x level instead of at the y level, that's going to have a horizontal effect. Now, with these, you have to be a little bit careful, because when the a is greater than 1, or the constant that you're multiplying here is greater than 1, it actually is going to have a horizontal compression effect, which will appear like a vertical stretch. These always work in opposite manner to each other. And when the constant that you're multiplying the input by is between 0 and 1, that's actually going to have a horizontal stretch effect, which will also appear as a vertical compression simultaneously. The last kind of transformation is the simplest one. That's when you basically just take all the outputs and multiply them by -1. So you're just going to basically vertically flip or reflect the graph. Let's quickly take a look at all these on Desmos for a better, more intuitive understanding. Okay, so here we can see the graph of y equals 2 to the x on the right here. So we'll take a look at y equals 2 to the x minus 3. So let me be lazy and copy that. All right, so if we just change the x to x, this is going to be a little tricky with Desmos. I'm going to have to use parentheses. So x minus 3. And notice that, in fact, let me change the color. It did move the graph 3 units to the right. Now, if we change that -3 to +3, you'll see that the graph of 2 to the x will move to the left 3 units. Now, if we actually change the function to and bring the change like here at the output level, so just add 3 to the 2 to the x itself, notice it's just going to move it up 3 units. And if we of course change that plus to a minus, that'll move the graph down 3 units. All right, so if we look at this vertical stretch example now, we have y equals 3 times 2 to the x. And notice that vertically the graph was stretched. It's as if you're pulling it up vertically by a factor of 3, like the 1 is now 3 as an output. However, when you look at it horizontally, notice that it looks like you actually compressed it, as we were mentioning earlier. These two work simultaneously and they have opposite effects. So if we were to actually, instead of stretching it vertically, if we were to go ahead and multiply by 1/3 instead, notice that the main graph 2 to the x is in red, and you can see the blue one has been vertically compressed. But when you look at it horizontally, notice it looks like you actually stretched it horizontally. So a vertical stretch and a horizontal compression go hand in hand. All right, so next, let's go ahead and look at the horizontal dilation. And here we're going to change 2 to the x to 2 to the 3x. Well, we're going to look at both. So, okay. So, remember we said that when it comes to horizontal compression or dilation, when this factor is actually larger than 1, it actually has the horizontal compression effect. And notice horizontal compression goes hand in hand with actual vertical stretching. Now, if that 3 is changed to 1/3, oh, not that. Let's see, 1/3. No, let's get rid of that. Notice that's going to have the effect of a horizontal stretch, which vertically, of course, it will look like a compression. See, it looks like it was vertically compressed. And once again, they go hand in hand. Finally, we'll take a look at the reflection. That's when we just look at y equals, we just multiply it by -1, so it becomes -2 to the x. And see, that one just flips it vertically. So that's called a reflection. All right, those are the various types of transformation you can apply to the exponential function. Okay, by now we have seen these kinds of transformations with both parabolas and exponential functions, but the nice thing about it is that what you have learned applies to all functions, so we can generalize this on the next screen. So in general, if you have a function f, and assuming that you know the graph of the function f of x, and if you choose some k value greater than 0, if then you want to obtain the graph of f of x minus k, you're simply going to shift the graph of f k units to the right. With x plus k, you're going to shift the graph k units to the left. If you have f of x plus k, you're going to shift it up k units. With f of x minus k, you're going to shift it down k units. Now, when you multiply f of x by k, you're going to vertically stretch if k is greater than 1. You're going to vertically compress if k is between 0 and 1. And of course, remember, every vertical stretch is simultaneously accompanied by a horizontal compression, and every vertical compression is simultaneously coupled with a horizontal stretch. For when you want to do a horizontal compression, you bring the change about by multiplying the k by the input x, and that of course will be coupled with a vertical stretch, and that's for k greater than 1 when k is between 0 and 1, and you multiply it by the input x, you're going to get a horizontal stretch, which is a simultaneous vertical compression effect. And of course, if you just simply want to flip the graph of a function, just multiply it by -1. Next, we're going to try to solve some exponential equations. We'll be looking at the simplest type in this section. These do not require the utilization of a function called a logarithmic function, or also a concept called the concept of logarithms. We can do these by just basic rules that we'll discuss in a second. The game plan is basically going to be this. We're going to deal with equations where this scenario is possible for them. That means we're going to be looking at exponential equations where it is possible to write the two sides using the same base. Once we have done that, because we know that the exponential function is 1 to 1, let's take a look at its graph real quickly. If you remember the graph of the exponential function which we saw earlier, clearly it passes the vertical line test, so it's most definitely a function. But notice it also passes the horizontal line test. You're not going to get any horizontal line crossing it more than once either. Because notice in this region, you may be thinking, oh, it looks like a horizontal line will cross it there. But no, there is always some angle here which is going to make every horizontal line cross it only once. Now, what's the significance of that? The significance is that if you have two inputs, outputs that are equal, that means they must have come from the same input. Because remember, with one-to-one functions, no two inputs have the same output. So if you have two values of b to the x that are equal, and then the inputs must have been the same. Let's go back to the equation we were looking at a minute ago. So if these two outputs are the same, that means the inputs x and y must have been the same because of one-to-oneness. We're going to be using this fact to solve certain types of equations where this becomes possible next. All right, so here we have an equation, 9 to the x equals 243. We're going to try to write both sides of this equation as powers, but with the same base. Now, it does look like we should be able to use the base 3 at the very least. So we are going to go ahead and look at the prime factorization of 243 to see what it looks like. Now we know that 3 goes into that 81 times. 3 again goes into it 27 times. 3 again 9 times. Remember, on the left side you only want prime numbers if you're going to obtain the prime factorization. 3 again will give us 3, and then one more 3 will give us 1. So it is 243 is definitely a power of 3. In fact, we know that now we can write it as 3 to the 5. But notice it is not a power of 9, because you have one 9 here and another here, but you don't have another one. So it's not a power of 9, but it is a power of 3. So we're going to go ahead and write both sides as powers of 3, because we already know that we can write 9 as a power of 3. So we'll go ahead and write 9 as 3 squared to the x, like that. And we'll go ahead and replace the 243 with what we now know to be 3 to the 5. So of course now we'll use the power rule to simplify the left side down to 3 to the 2x. And on the right side we have 3 to the 5. Now we have the form that we're looking for. We want b to the x equals b to the y, so that we can from there conclude that x must be equal to y. So at this point we go ahead and say therefore, and this is, again, if you want to give the reason, it's by one-to-oneness of the exponential function 3 to the x. F of x equals 3 to the x, so we get 2x must be equal to 5. Be very careful here. This is not a simple dividing both sides by a number or multiplying by a number. It's not a basic operation. This is a complex deduction based on a complex understanding of the one-to-one nature of functions. So make sure you're not experiencing the error of thinking we're canceling the 3's or anything like that. That is not what's going on here. So then finally we just get x equals 5 over 2. And that should be it. Now it's easy to check the answers. You can just plug into the original equation 9 to the 5/2. See that if that gives you 243. And of course that's going to be the fifth. Actually, the square root of 9 to the 5. You want to know if that's 243. Remember, we have a nice rule that says if you have the nth root of x to the m, you can take the nth root of x first and then raise it to the power of m. That's going to help us here, because we're going to take the square root of 9 first and then raise it to the power of 5. See if that's going to give us 243. And of course, square root of 9 is 3. We want to know if 3 to the 5 is 243. And if you notice, we verify that here. So at this point, our next line is going to be 243 equals 243 with no more question mark needed because we have verified it. So now we can write the solution set professionally as solution set contains 5 halves. Just wanted to demonstrate that for you. We won't be taking the time to check every one of these because otherwise the video will go on forever. But you should definitely do that for yourself. That's always good practice with radicals and similar skills as well. Okay, so here we have another one of these, and of course, if you recall when we did a video on powers, I gave some tables out for you to memorize, because being familiar with these powers, at least for each table, like for example for squares, you'll want to know probably up to 12 or 13. But for the rest of them, you should know at least the first 4 or 5 powers. Like say for cubes, you should know cubes up to like 5 cubed. You should know fourth powers up to probably 5 to the 4, etc. So this will make you very sharp with this kind of problem, and also it'll help you recognize the bases that you're going to need. Here, I think it's pretty clear that we're going to need to use the base 5. So we'll go ahead and write 25 as 5 squared to the x, and we'll write 125 as 5 cubed. Of course, you know 125 breaks down with 5 giving you 25, another 5 giving you 5, and one last 5 giving you 1. So 125 is the same as 5 cubed. So we get 5 to the power of, let's not forget the x plus 5 here. Okay, so we get 5 to the 2x equals, now that 3 and the x to the 5 need to be multiplied. Of course, we're using the rule that says x to the m to the n equals x to the mn, also known as power rule. So we get 3 times x plus 5. Now we have the scenario we wanted. We have 2 powers here. They have the same base, so b to the x equals b to the y. We're going to deduce that x must be the same as y. So now we can say 2x equals 3 times x plus 5. So now we just have to solve that simple equation, which is linear. So we get 2x equals 3x plus 15. Let's go ahead and move the x's to the right side to get 3x minus 2x. We'll move 15 to the other side, it becomes negative 15, so we get x equals negative 15. And that is the number that's going to do the trick here. Now, of course, with an answer like this, checking by hand would not be the simplest thing in the world. So you can always bring up a calculator and check using a calculator. So let's do that. All right, so here what we'll do is we'll go ahead and type 25 to the power of x, which is negative 15. That's our proposed solution. And we'll go ahead and hit enter to get a value. Now that's a very, very small number, as you know. So now what we'll do is we'll go ahead and compute the right side, which is 125 to the power of x plus 5. So negative 15 plus 5. And we notice that we get exactly the same thing. So we know we have done it correctly. We go ahead and write the solution set. When you write the solution set, don't bring the x, just the numerical value of the particular x value that works. And that's how you do a problem like that. Make sure that every single one of these, if we're done, if you didn't get it on your own already, that you do it on your own and make sure that you can comfortably go through all the steps. Don't come and unpause and go to the next problem until you do, because otherwise optimal learning is not taking place. And of course, it goes without saying that as soon as you do see a new problem, you should definitely pause the video and try it on your own before you come back to watch the rest. All right, so here we can see that 2 is a good candidate for our base on both sides. So we'll go ahead and write the 8 as 2 cubed, and we're going to raise that to the power of 3x minus 4. And we're going to write the 16 as 2 to the 4. And of course, we need to raise that to the power of 2x plus 3. All we did was replace 8 with 2 cubed and 16 with 2 to the x plus, with 2 to the 4. All right, so we get 2 to the power of 3 times 3x minus 4 equals 2 to the power of 4 times 2x plus 3. So we get 2 to the power of 9x minus 12 equals 2 to the power of 8x plus 12. So now we're going to go ahead and set those equal to each other, those two exponents, because of the one-to-one nature of the exponential function. So we get 9x minus 12 equals 8x plus 12. So if we move the x's to the left side, we get 9x minus 8x equals 12 plus 12. So we get x equals 24. All right. So let's go ahead and run a quick check on it, make sure that it works so that we didn't make any quick errors. So we'll go ahead and remember, you always want to check in the original equation. So we're going to go ahead and type 8 to the power of 3 times 24. We're replacing x in the original equation with 24. And we go ahead and subtract 4. So that's 3 times x minus 4. And we get this value. This time that's a huge number. And now we're going to go ahead and evaluate the right side, which is 16 to the power of, okay, we need to do the power. So to the power of 2 times 24 plus 3. And we go ahead and hit enter and hope that we get the same thing. Of course we did. So we're good to go on that one. All right, so now we're going to write our solution set, which is going to contain 24. As always, make sure you can do it on your own before we proceed. All right, so for this next one, give it a try, see what happens, and then come back. All right, we'll come back. If you're familiar enough with powers, you should recognize both 8 and 128 as powers of 2. 8, of course, we know is 2 cubed, and 128, if you just do a quick prime factorization, you get 2, 64, 2, 32, 2, 16, 2, 8, 2, 4, 2, 2, 2, 1. So you can see there is 1, 2, 3, 4, 5, 6, 7. So 128 is the same as 2 to the 7. So we're going to go ahead and write the 8 as 2 cubed like this. We need the x on the outside as a power, or the exponent, and down on the other side we're going to write 1 over 2 to the 7. So we get 2 to the 3x. All right, we certainly don't want to leave this 2 to the 7 down here because we want to have the same base, and this is not going to cut it. So we're going to use this rule, 1 over x to the n equals x to the negative n, to go ahead and bring that 2 up. So that becomes 2 to the negative 7. Now we have the form that we want. So now we're going to go ahead and conclude that therefore 3x must be equal to -7. So we get x equals -7/3, like so. All right, let's go ahead and do a manual check on this one. We want to know if 8 to the power of -7/3 is equal to 1/128. So, of course, we know that 8 to the -7/3 is the same as 1/8 to the 7/3. We want to know if that's equal to 1/128. So we know that that can be written as 1 over the cube root of 8 to the 7, and we want to know if that's the same as 1/128. And we know the nice rule that tells us it's okay to take the cube root first and then raise to the power of 7. That really makes calculations much simpler. And continuing on the right, we know that the cube root of 8 is 2. So now we're down to this. Is 1/2 to the 7 the same as 1/128? Well, if you know this, we've already shown that 2 to the 7 is 128. So finally we get 1/128 equals 1/128. We no longer need a question mark because we have verified. We did need it over there. All right, so at this point, make sure you keep question marks until the last step where you either show that they're equal or that they're not. In either case, you can drop the question mark because by then you know. But until then, you're verifying, you're not asserting, so you do need the question marks. All right, so that's that, and we'll go ahead and write the solution set. We have one solution, and that is -7/3. All right, so make sure you try that before we move on. All right, this is actually going to be our last one, so definitely give it a shot, see if you can get it on your own, and then come back. All right, so 125, I know that is a power of 5, right? 5 cubed. 216, I know what it is, you may not. So let's look at the prime factorization. This is the good news. Even if you don't know these things, if you take the time and find the prime factorization, you can always find it. So 2 gives us 108, 2 gives us 54, another 2, 27. Now we go to 3, which gives us 9, 3 again, 3, and finally one last 3 gives us 1. Now we notice these nice pairings of 3 6s, right? So you can see that 216 is the same as 6 cubed. So we have 5 cubed down on the bottom of that fraction, and we have 6 cubed on the top. So let's start with that, see where we can take it. So we have 5/6 to the x equals 6/5 cubed. Now, that's almost what we like, right? We actually want to have the exact same base. So one of these has got to change itself. And how? Well, remember, we have a nice rule that if you have x/y to the -n, that's equal to y/x to the n. You always have to learn mathematics formulas left to right as well as right to left. Some people only learn it in one direction and then they won't know how to apply it when it needs to go the other way. So one useful way of doing that is to actually write it from right to left with the right side on the left, in case your mind just likes to function that way. This way you compensate for that. So I just wrote the exact same equation. I just wrote this side on this side, and I wrote the left side on the right side. So you see, you should be able to apply this. Now, I can do it to the left side or the right side, but usually I like to leave the x alone. Don't turn it into a negative x, so we'll do it to this side. So we go 5/6 to the power of x equals 5/6 to the power of -3. Now we have the exact same base on both sides, so we can say therefore x equals -3. And checking this is actually very fast, so let's go ahead and do it. We want to know if 5/6 to the -3 is the same as 216 over 125. Now, of course, 5/6 to the -3 we just learned is the same from this rule. Now we're going to go from left to right. We know that it's going to be the same as 6/5 cubed. We want to know if that's the same as 216 over 125. Of course, we know what 6 cubed is because we worked it up up here. So we have 216, and we know that 5 cubed is 125. So we get 216 over 125 equals 216 over 125. We no longer need the question mark. It has been verified. So now we can confidently say the solution set contains the x value -3. All right. Next, we want to talk about an extremely important number in mathematics, finance, and many sciences called the Euler number, whose value is approximately 2.7, and it's attributed to the brilliant Swiss mathematician Leonhard Euler. Even though we have referred to y equals 2 to the x as the reference exponential function, 2 is actually not the most important base for an exponential function. That honor goes to the Euler number e. The Euler number e is a mathematical constant that is approximately equal to, as I said, around 2.7, and it is the sum of this infinite series from n equals 0 to infinity of 1 over n factorial, which basically means 1 plus 1 over 1 plus 1 over 2. This is, of course, 2 factorial plus 1 over 3 factorial. When you have a factorial after a natural number, it just means start with that natural number and start multiplying by the next lower one and the next lower one until you reach 1. And this continues forever. And you end up with that sum. It can also be calculated using this limit. The limit as n approaches infinity of quantity 1 plus 1 over n to the n. Now, infinite series of this type, as well as limits at infinity, will be studied in calculus. But we can still use the Euler number e to handle some exponential growth and decay problems without fully understanding the series or the limits of this type. Now, alongside pi, the other famous constant that we know about, the Euler number e is an important number in, as I said, math, finance, various sciences. It is also used to represent the base of the natural logarithm, which we will study soon. One of the financial applications of e is in continuous compounding, which is a method of calculating interest on a loan or investment for which interest is compounded continuously. Basically, always remember, you want to borrow in a simple interest scenario, and you want to lend at a compound interest scenario. In other words, when you put some money in the bank, you're lending the money to the bank, and you want to make sure that they're paying you compound interest, which most banks do. Unfortunately, however, when you borrow money as well, they're also going to charge you compound interest. So it's a give and take. Continuous compounding is a process where the interest earned on an investment or loan is calculated and added to the principal continuously, rather than at fixed intervals. The formula for calculating the future value of an investment with continuous compounding is given by A of t equals PE to the RT. It's the famous PERT formula. Some people who may remember the shampoo PERT, we used to help that as a mnemonic for students. I don't think it's quite as popular as it used to be. Where A is the future value of the investment, and P is the principal amount or the present value, R is the annual interest rate, and T is the time period in years. E is, of course, the mathematical constant we just learned about, the Euler number. In general, any quantity that increases or decreases exponentially with the base E is given by the formula, which is very similar to that formula. A of t equals A0 e to the kt. Here, A of t is again the future amount. A0 is the initial amount of whatever substance we're studying. E is the Euler number. K is what's called the either the growth constant or the decay constant, or also the growth rate or the decay rate, depending on whether it's greater than zero. If it is, it becomes the growth rate, and if it's less than zero, it becomes the decay rate or the decay constant. And t is the time period of growth or decay. And we'll be looking at both of those formulas in more detail in our examples. Next, to give you an idea of what the graph of y equals e to the x looks like, as you would expect, it looks very similar to 2 to the x and 3 to the x, which we've already seen. And again, as expected, it falls somewhere in between. Remember, the value of e is about 2.7, so you would expect it to fall somewhere in between these two graphs. Notice that all of them have domain, which is the set of all real numbers. All of them have range, which is the set of all non-negative real numbers, in other words, bracket 0 to infinity. And they're all increasing over their entire domain. As x approaches negative infinity, they all approach 0. So therefore, the x-axis plays the role of a horizontal asymptote for all of them. They all go through this point 0, 1, because of course it doesn't matter if you're looking at 2 to the 0, e to the 0, or 3 to the 0. They're all going to be 1. So they all go through the point 0, 1. And as close as 2 to the x and 3 to the x are to this graph, they didn't make the cut. This is the magic one. This is the one that is used in all exponential growth scenarios of any significance to us. So, but you can see the graph is just a regular exponential graph like either one of these two. Next, we want to take a closer look at periodic compounding and continuous compounding. The formula that we saw, the nice simple PERT formula, A of t equals PE to the RT, actually comes from the periodic compounding formula. So it would benefit us to actually understand where the periodic compounding formula, which is this more involved formula down here, not as simple or elegant as A of t equals PE to the RT, but very important, comes from, because we need to know this before we can really get to the other formula. All right, so let's suppose that you invest P dollars, P for principal, in an account that pays 10% interest that compounds quarterly. That means 4 times a year for 1 year. Now, this could have easily been, instead of investing, it could have been you took out a loan. It doesn't make any difference. They're both going to, the total amounts are going to be calculated the same way, except that in one case, you're being paid. In another case, someone else is being paid, right? So at the end of the first quarter, you're going to have however much you started with, right, plus you take the interest rate, which, 10%, you always want to write it as a decimal when you use it in the formula. And of course, since we're paying interest 4 times, you're not going to get paid the whole 10% at the end of the first quarter, right? You're going to get paid 1/4 of that 10%, and you're going to multiply that by P, right? Again, it's going to be this interest amount rate times P. So if you factor out a P, notice that you end up with 1 plus 0.01 over 4, and I put a 1 here for emphasis. It'll become clear later why I put it there, because I mean, obviously you can raise anything to the power of 1 and it stays the same. All right, for the end of the second quarter, remember, this is compounding interest, so that means they're going to pay you interest not on the original amount P, but on where you started the second quarter with, which was this amount, which is how much you had at the end of the first quarter, right? So you start with that amount from right here, and you're going to add to that again 1/4 of the 10%. So this time it's going to be multiplied by this starting amount, right? Times that. Now watch. This expression here, P times 1 plus 0.1 over 4, is now a common factor of these two terms. Remember, there's one term right here and there's one term right there. So we factor that out, and again, that leaves us 1 from here plus this quotient or this fraction from here. So we get this amount times 1 plus 0.1 over 4, right? Which becomes P times a product of two of those. So that becomes 1 plus 0.1 over 4 squared. Now, so this is the end of the second quarter, which means the beginning of the third quarter, right? So now they're going to pay you interest on this amount. So you're going to start with this, and then you're going to again take 0.1 over 4 and multiply it by that amount, right? So again, we're going to factor out this expression, which is common to both terms, and that leaves us what? 1 from here plus 0.1 over 4 from there. So we end up with what? The original P times 1 plus 0.1 over 4 cubed. And we do it one more time at the end of the fourth quarter. Again, this time, remember, this is the starting amount, the P times 1 plus 0.1 over 4 cubed. And we're going to pay how much? 0.1 over 4 of that amount, obviously. So this time we're going to factor out the P times 0.1 over 4 cubed, and that leaves us 1 from here plus 0.1 over 4 from there. So we're going to end up with P times 1 plus 0.1 over 4 to the power of 4. Now, of course, if let's say you were doing it for another year, this would keep going, and what would that exponent be at the end of 2 years? It would be 8, right? So it would be 4 times 2, right? So 4 times the number of years, right? If it did it for another year, the last exponent would end up being what? 12, right? So that is where this formula comes from. So the amount that you're going to have at the end of t years, it's going to be your initial amount P times 1 plus r over n. That's like our 0.1 over 4 to the power of what? nt. Where is n? N is the number of periods of compounding. Here we had 4, but let's say you have more than 4 or less than 4. It doesn't matter. You would use the number there and multiply it by the number of years. And that's where that formula for, this is called the formula for periodic compounding, comes from. Now it can be shown using calculus techniques that if we take this formula that we just came up with, a of t equals p times 1 plus r over n to the nt, and let the number of compounding periods n go to infinity, we will obtain the continuous compounding period formula, which is a of t equals pe to the rt. No period here. I don't know why I put that there. Let's get rid of it. There we go. That's better. So it's just called continuous compounding formula. All right. So a of t equals pe to the rt, which we have already seen, right? All right. Now we have two kinds of formulas that we can use then. If there's a fixed number of compounding periods, a finite number, then we use this formula. But if interest is being compounded continuously, then we use this formula. Let's go ahead and take a look at this a little deeper. So remember, compound interest comes in two flavors, right? Periodic compounding or continuous compounding. For periodic compounding, interest is earned a finite number of times per year. For continuous compounding, interest is earned an infinite number of times per year. That means at each instant. Now, if you have this scenario where there is periodic compounding, you're going to use this formula. Again, a of t is the future value after t years. P is the present value. That means at the inception or the beginning of the investment or loan. N is the number of compounding periods. That means that the times interest is added each year, the number of times. Missing number here. And T is the number of years of investment or loan. The much simpler continuous compounding formula, A of t equals PE to the RT, is what you use if interest is being compounded continuously, and you end up with A of t equals the future value, of course, as before. P is the present value, which is at the inception of the investment or loan, and T is the number of years of investment or loan. Let's go ahead and do a few application problems to bring all this to life a bit. Okay, so in this problem, we want to find the future value and interest earned if $10,000 is invested for 9 years at 7% compounded once semi-annually and then continuously. So these are two different problems that we're going to be looking at, right? Now we know that for semi-annually, that means a periodic compounding scenario, so we're going to be using this formula. And for continuous compounding, we know that we need to use this formula. So let's go ahead and use them and we'll see what we have. So obviously 10,000 here is going to be P, right? And we have R. Remember, we're always going to represent that using a decimal, so it's going to be 0.07. And T is equal to 9. And for this particular case A, semi-annually means twice a year, right? So N is 2. All right, so we go ahead and we calculate A of 9, basically, right? It's a function of T, and T is time, right? In years in this case. So we get P, which is 10,000 times 1 plus 0.07 over 2, which is n, the number of compounding periods, to the power of 2 times 9, right? N times t. All right, so at this point, all we have to do is plug it into the calculator, let it do the crunching for us. All right, so we're just going to type it in case you're wondering why I have two keypads here. I love this calculator. It's absolutely fantastic. However, it doesn't have the most responsive keys. This numpad here has a much better response. So here we go. So we're just going to type in 1,000, 10,000, right? Okay, I thought I had jinxed it there for a minute because it wasn't typing at all, but I think it's working now. So 10,000 and then times 1 plus 0.07 over 2, and then we need to get out of the fraction so we can enter our parentheses, and then we're going to raise to the power of 2 times 9. Of course, we can just put 18. All right, and then we hit enter, and there's the amount that we will have at the end of 9 years if we invest the $10,000 at 7% semi-annually. All right, so let's go ahead and take a note of that. So A is we're just going to round to the for money. It doesn't make any sense to go more than 2 decimal places, right? So A is approximately $18,574.89. All right, now we'll calculate the other side, the continuous compounding side. That's a much simpler formula. So of course, notice that for part B, P, R, and T are the same. We just don't have a number of compounding, finite number of compounding periods. So those three apply here as well. So we get A of 9 equals 10,000 e to the power of 0.07 times t, which is 9. All right, so now we go ahead and compute that. So 10,000 e. Now you notice there's an log and an ln. Okay, ln is just the natural log, which is log base e. Now you will understand all this very soon very well. So but just remember, it's going to be the second function of ln, which is e. So you're going to want to go shift ln. Now that just gives you e to the power of, and it's ready for you to type in the exponent, right? So which is going to be for us 0.07 times 9, just like that. Okay, so let's see, it doesn't like something that I put in. I think I put an extra dot or something. Let me fix that. All right, it was having one of its touchy moments. As it turns out, it wanted me to put in times after the 10,000. You know, sometimes it does this, sometimes it doesn't. So but here we go, it's no big deal. So we just put shift ln e to the power of 0.07 times 9, and we get that. So we get approximately 18,776.105. So we'll just round it to 0.11. Now clearly, as you can see, you are going to end up with more, but you may be surprised that it's not a lot more, right? You're going, right, this one is, you know, earning interest continuously. How could it be relatively comparable to this one that's only earning interest twice a year? But remember, this one is going to earn a much bigger chunk every time it gets paid, right? Whereas this one, at every instant, is just going to add a very, very tiny amount, right? So yes, in the long run, this will end up, paying you more. And obviously, who doesn't like an extra couple of $100? And that's just on $10,000, right? Imagine if the investment is much larger, right? You're definitely going to go with continuous compounding. And as it turns out, most banks, are both borrowing and lending using the continuous method. So yeah, so it does definitely make a difference, but not as much as some would expect. All right, so very simple but important problems. So make sure you know how to do these. We'll proceed. All right, so for our next problem, we have find the present value that will grow to $24,000 if interest is paid at 7% compounded quarterly for 14 quarters. Now, they're not giving you the number of years, but they're giving you the number of quarters. So it doesn't matter. We can figure it out. Now, notice that in this problem, we're not trying to find the future value. We know the future value. So let's write the formula down and we'll then say, write down what we have, okay? So notice that this is periodic compounding, right? Because we have a finite number of compounding periods. It's quarterly, which means 4 times per year. So we're going to be using our formula that relates to periodic compounding. Let me bring that over. It's much nicer in that format. Okay, so there's our formula. So we know that A of t is given. That's 24,000. P is what we're trying to find, so that's our unknown. We know R, 7%, so we're going to use 0.07. And for the number of years, T, we know that it's going to be 14 quarters, right? So basically 14 over 4 years. All right. So because remember, that's a let me make it more clear for you so you understand. Because that's a quarter of a year, right? So that's how you end up with 14 over 4 years. All right. Now, we're going to plug in everything that we know. So we know that 24,000 equals P times, we didn't write the number of compounding periods. Remember, that's going to be 4. Quarterly, that means 4 times a year. So P times 1 plus 0.07 over 4 to the power of n, which is 4 times t, which we calculated is 14 over 4. Now notice these 4's of course will cancel out, so we'll just end up with 14 for the exponent. So we get 24,000 equals P times 1 plus 0.07 over 4 to the power of simply 14, right? So P is the unknown. What do we have to do to get it by itself? Basically divide both sides by this expression and you'll have it. So we get 24,000 over 1 plus 0.07 over 4 to the power of 14 is going to be P. So now we just have to compute that. All right, I'm just gonna put up with the keyboard on this. So we get 24,000 divided by 1 plus 0.07 over 4. We need to exit and raise it to the power of 14. So just double check, make sure you've typed everything in correctly. Take a few seconds to do that. Always pays off. Better take 5 seconds to check than lose 5 points, right? All right, so there we go. So that's going to be obviously an approximation, so we'll change that to the correct sign, and we'll say 18,824. Point, remember, with money we'll only go to 2 decimal places because that's all that makes sense, because we only have pennies, right? So 7 6. All right, so that would be the present value needed in order to end up with $24,000 at the end of 14 quarters if it pays at 7% interest rate. All right, so that's how you do that one. All right, so here's one where the annual interest rate is what's going to be the unknown. So we'll handle it in, pretty much the same way using the same formula, because again, it's going to be a periodic compounding situation. All right, so once again, that's the formula we're going to use. Let's see what we have here. So there's a percent for 1100 to grow to 1700. So we know that A of t, the future value that we want, is 1700. The present value that's been invested is 1100, right? And if it's compounded quarterly, so we know n equals 4. Just so you know, semi-annually, that's 2 times per year. Annually, of course, that's 1 time per year. Monthly, that would be what? 12 times per year, etc. I believe that when banks, for example, would say daily, they consider the year to be 360 days, just to simplify matters. All right, so in case you see that, don't be surprised. Even though we know, of course, a year is 365 days. All right, so n equals 4 here, and t is 8 years. So we'll just use 8. So we plug in 1700 equals 1100 times 1 plus r over 4 to the power of nt, which is 4 times 8, right? Nt, so 32. All right, so basically the r that we're looking for is kind of trapped inside this group here. So what we need to do is we need to go ahead and isolate this power first, the whole power. So we'll go ahead and divide both sides by 1100. So we get 1700 over 1100 is equal to 1 plus r over 4 to the power of 32. Of course, these zeros cancel out, so we just end up with 17 over 11 equals quantity 1 plus r over 4 to the power of 32, right? So now, in order for us to be able to get this outside of this prison, we're going to have to raise both sides to the power of the reciprocal of that, because we're going to be using the power rule, right? We know that x to the m raised to the n equals what? That's called the power rule for exponents. You know that you multiply, right? So if I have x to the power of 32, right? What would I have to raise it to the power of in order to just get x to the power of 1? Remember, that would have to be 1 over 32, right? Because then 32 times 1 over 32 is 1. So that's what we're going to have to do to get rid of that 32. So, well, on the right side anyway. It won't just go away, right? Okay, so basically we're going to raise both sides to the power of 1 over 32. So what that leaves us on the right side, of course, is just 1 plus r over 4. And what it leaves us on this side is 17 over 11 to the power of 1 over 32, which is, of course, the 32nd root of 17 over 11, right? But we can just type it in as is. We don't need to convert it to a root. So now we get r over 4 equals, we're going to move that 1 to the left side, so we get 17 over 11 to the power of 1 over 32, and then minus 1, right? So all we have to do now to get r by itself, let me go over here. So we get r equals, multiply both sides by 4, right? Don't forget to use parentheses because it's going to have to get distributed since there's more than one term involved here, right? So 17 over 11 to the 1 over 32 minus 1, like so, okay? So now we're just going to type that in. That's all there is to it. So we get, let's clear all that a little bit. So we get 4 times, and we're going to want another pair of parentheses for 17 over 11. We're going to exit the first set of parentheses and type to the power of 1 over 32. And then exit the fraction and then exit again, so that now you are ready to type in your minus 1. And that should be it. Just double check, make sure you've typed in everything correctly. Hit enter. So you get r is approximately 0.05. Let's go, we'll go ahead and one more place, 5.5, okay? Because now we're going to, if you're going to answer it as a percentage, you know how you go from decimal to percentage, right? Easy. Just take the 0.055 and multiply it by 100%. That's how you can go from pretty much any numerical format to percent. Just multiply by 100%, because 100% is 1, of course. And you can always multiply any number by 1, right? The trick is, though, we keep the percent and just multiply that part out. So we get what? So we get 5.5%. Now this I can say equals 5.5%. Of course, this equal doesn't mean that my answer is not approximate. As long as you have a chain of signs, as long as there's one approximation, that means your final answer is an approximation. So I'm just saying 0.055 itself does equal exactly 5.5%. That's all. All right, so that's the interest rate that would be required for 1100 to grow to 1700 if compounded quarterly for 8 years. All right, so make sure you can carry that on your own, and we'll proceed. All right, here's one last problem for the road. Bank A is lending money at 6.8% interest compounded annually. The rate at Bank B is 6.7% compounded monthly, and the rate at Bank C is 6.75% compounded quarterly. Which bank will pay the least interest? Would you pay the least interest if you were borrowing, of course, right? So not the bank will pay, but will you pay the least interest too? Now I just wanted to show you this one just because it almost like you're like, wait, there's not enough information. What's the initial investment amount, etc.? Well, it doesn't really matter, I mean, you could, for example, pick your P to be 100, your present value to be 1,000, 10,000, makes no difference. Or you could just leave it as P. Why don't we do that? Because I think it's good to be able to work a little bit abstractly. So let's say that you're borrowing P dollars for 1 year from each of these banks, right? What would you pay this bank? What kind of total at the end of the year, right? For Bank A, let's see. Remember, Bank A is charging 6.8%. So in other words, we have R equals, remember, move the decimal 2 to the left and remove the percent. So 0.068, right? That's the rate you want to use in your formula. Compounded annually. That means what? That means n equals 1, right? Let me put that formula down for you once again. Okay, there's our formula. Now, as far as how many years should you calculate, it doesn't make any difference either. You could do different number of years or just do it for 1 year, right? Because that'll be giving you enough information to see which bank is going to be charging you the least interest. So we'll just let T be 1. So we have the P, we're just using P itself. R we have, N we have, and T we have. So we're ready to go ahead and calculate. So we get P, A of 1. So at the end of 1 year, you will have paid P times 1 plus 0.068 over 1, right? Over n, which is 1, to the power of nt. So 1 times 1, which is what? 1. So A of 1 would be 1.068 P. So that's the total amount, not just the interest, be careful. That's the total amount you would pay at the end of that year, by the time you've completely paid off the loan. All right. So how about at Bank B? How much would you be paying at the end of the year to Bank B if you borrowed from them? Well, remember the rate there is 0.067, right? It's compounded monthly. So N equals 12, right? And again, we're going with 1 year, so T equals 1. So for Bank B, A of 1 would be P times 1 plus 0.067 divided by 12, which is N. to the power of nt, right? So 12 times 1, which is 12. So let's go ahead and calculate what this amount is, right? So 1 plus 0.067 divided by 12, exit all that, and then to the power of 12. So we get approximately 1.069 p. That's the total amount you would be paying at the end of the year to bank B, right? And for bank C, they're charging 6.75%, right? So that means 0.0675, right, as a decimal. And they're compounding quarterly, so that means n equals 4, right? And of course it's for 1 year again. So a of 1 for bank C would be p times 1 plus 0.0675 divided by 4, which is the number of compounding periods n, to the power of nt, 4 times 1, which is what? 4. So now we'll go ahead and compute that. So I'm going to be a little lazy, just copy that and change some numbers. So I'm going to go put 4 there. I'm going to go to the top and change that to 0.0675. Right? And I'm going to change the 12 to 4. Right? Double check. 1 plus 0.0675 over 4 to the power of 4, right? So we get approximately 1.069, right? Now, because of times p, right? Now, because these two ended up being the same, I should probably take one more, go one more place, right? It doesn't really matter. I'll explain to you in a second why. So that would be a 1, and this one would be 2. Doesn't really matter because we're trying to find where you're going to be paying the least, and we already know that it would be this one, right? Because these are both in the 6-9 period, right, area. So we already know that this number is the least. That means if you're paying the least total, that means you've paid the least what? The least interest, right? So I mean, what if you wanted to know what the amount of interest is? Very easy, right? Just take that amount and subtract p from it, right? So that's just going to be 0.068p, right? Or this one will end up being, the interest will be 0.0691p. For this one, the interest would be 0.0692p, right? So basically, which bank will you pay the least interest? You would pay bank. So the winner is bank A. All right. Now, if they were offering you savings account opportunities, obviously, right? And paying in this way, you would go for which one? You would go for bank C, because you would want to make the most money, right? So there's competition going on at all times. All right, so there are some applications that hopefully bring this home a little bit for you, and that should do it for this video. Take care until the next one.